Okay, hi guys. So today we'll be solving Leetcode daily prop, shortest subarray with some at least k. So it's fairly simple. So we're given an integer array norms and an integer k. Need to return the length shortest non-empty subarray of norms with a sum of at least k. If there's no such subarray, we return -1. And a subarray is a contiguous part of an array. So the first intuition when after reading the problem description is actually a sliding window technique, right? So in short, we will slide our right pointer to up to a point where it surpasses k result, right? Yeah, for example, we will like our left and our right is here, and we will slide here, and we slide here, right? Now our the current sum is 3, right? And then we will start moving our left pointer until up to a point where we can move our left pointer anymore, since it will make the total sums less than k. But this approach is actually it's not going to work for this problem, right? Why? Because here you can see that in our array there is negative numbers, and this could harm like the process of defining the right pointer, right? The stop point where we need to like keep moving our left pointer, right? And also the binary search with fixed sliding window technique will not work because of that reason. As you can see here, I have 5 wrong submission for this problem. It may seem easy, but it is not. As you can see, the acceptance rate is relatively low, right? Okay, so how can we do this problem? What is the alternative if we don't use sliding window technique, or we don't use 2-pointer binary search? What is the technique that we will be using for this problem? Okay, so here's a catch, right? Basically, for we can treat each of these index as an ending point, right? Okay, so for example, this can be an ending point, this 2 can be an ending point, and then we will start looking at all of the prefix before it, prefix sum, right? What is the prefix sum that is actually is going to be minimum, right? What is the minimum prefix sums that appear before these 2, and it has the biggest index, right? So our algorithm will look something like this. We come to this point, we will add this point into our min heap, right? Our min heap will look something like prefix, sum, and index, right? And if we are at index I, we will add prefix sum of I plus I minus 1, and I minus 1 into our min heap, right? And then we will keep popping out element from our min heap up until a point where we cannot pop anything out anymore, because if we pop it out, then it will make the total sums less than k, right? And out of all these possibilities, what is the max index, right? And we will use that max index to determine the shortest length of subarray if we choose this index as the ending point, right? Okay, so that is the approach. It will be if the nums length is equal to n, then the time complexity will be O n log n, and then the space complexity, since we have to maintain a heap, it will be O of n, right? Okay, so let's start implement it. Length of nums, heap q, let's say q, prefix sum. Let's build our prefix sum array for I in range length 1n. Nums I plus prefix sum minus 1, right? Okay, so now we have our prefix sums. We will initialize our result value. I set it to a very big int, a very big number. After that, for I in range length range n, if I is larger than 0, we will push the prefix sum at I minus 1, and then the index I minus 1 into our queue, right? After that, let's say y q n prefix sum I minus q00, which is the prefix sum at some index before I, right? Is actually larger or equal to k, mean we can actually still pop some element out, since it still satisfies the constraint, right? Okay, so say that the index is 0, right? So the index is actually at 0. Okay. Okay, so we only care about the index, right? Current index would be equal to max index, current index. Why max? Because we need to find the prefix with that has the largest index, right? That will make the subarray the smallest. Okay, so what are we popping out? We are popping out the subarray ending at j position, which appear before I, that is going to be excluded from our subarray until I, right? So is in order for a subarray ending at I to be the shortest, we will need this j to be the largest, right? Okay, after that we will have our index. Let's say that if prefix sum is not 0, result will be equal to min result, and then I minus index plus 1. Right? Okay, so we will, for example, we are here, we exclude these subarray out. That is going to be 1. This is 2. 2 minus 1, right? So we don't need to plus 1 here. If ending at a position where the prefix sum is already larger than k, but we cannot actually popping any element out, we will say that if prefix sum at I is actually larger or equal to k, result will be equal to min result I plus 1, right? And then in the end we just return minus 1 if result is not float. Okay, let's submit it. This is all minus 1. This is bad. Let's see. It means that we don't have anything in the queue. Probably. Oh, we do. Isn't it issues? This is 3. Max. Okay, let's submit it. Okay, so as you can see, it's pretty efficient. This is a strong number. I don't care about it. It's actually still on log n, since we need to traverse the array nums one time, and then for each of these we will do a heap push and also heap pop for a min heap with, in the worst case, with the size of n, which is equal to the length of nums. That is going to be on log of n, right? And then space complexity, since we have to maintain a heap, is going to be on. Okay, so that's it for today, and I hope you guys understand the solution, and see you guys in next video.